Hello, welcome to AB Video 7.2C Part 2, End of Volumes by Revolution by Disks and Washers. So now we're going to take region 2, which is the region between the parabola and the line, and again we're going to rotate it over x equals 1. So again, vertical axis of rotation, horizontal strip within the shaded region. It's going to be a washer again because there's this big gap here. So you take that little spot from here to here, that length from here to here, reproduce the r, reproduce that little length, and there you have it. Your height is dy, pi big R squared minus little r squared. Since that's y, that's got to be from y equals to y equals, bottom border y equals 0, top border y equals 1. Now, for the radii, the big radius goes from here to here, which up here means from here to here. So what you're going to have to do is take 1 minus this. Now this right here, I'm going to call that x1, okay? Because it's on the green line, so it's green. Now the x coordinate on the green line y equals x is equal to the y coordinate. Now the small radius is this blue region right here, which will be 1 minus the x-coordinate on the blue curve. Well, the x-coordinate on the blue curve is y equals x squared, which means x equals positive root y. As you can tell, these are all above the x-axis. So I can replace that x by root y. Drawing is important. Okay, determine which value best approximates the volume of the solid generated by revolving the region bounded by the graphs of the equations in the x-axis. And again, make your selection based on a sketch. So we have y equals arctan, y equals 0, x equals 0, x equals 1. So hopefully you know that arctan looks like this. And has a horizontal asymptote of y equals pi over 2. So it's bordered by this blue curve, y equals 0, which is the red x-axis, x equals 0, which is the green y-axis, and x equals 1, which is this black vertical line. So you can see that I have this region here, okay? So what I'm going to do to approximate is I'm going to say, you know what? If I just draw this straight segment, it's as if I'm taking this triangle and rotating it on the x-axis, okay? Well, if you take a triangle and rotate it on an x-axis like this, so if I take that triangle, all I'm going to get very simply is a cone. The formula for the cone is 1/3 the formula of a cylinder. So the r, the radius, so if you come back over here, your radius is this height right here, which is this height right here, which is pi over 4, because if you plug 1 into inverse tan, you have the inverse tan of 1, which means the angle whose tangent equals 1, which is pi over 4. The height of your cone is this height right here, which of course you can tell is 1. And so that gives pi over 3 over 48, which is approximately 9/16. Okay, so the closest one to 9/16, which is, close to 8/16, would be 3/4. The others are all wrong. I believe this is the last one, and it is not. There's one more after this, sorry. Okay, so here, this is a kind of an AP type complicated question. A glass container can be modeled by revolving the graph of this, a very attractive piece function about the x-axis, where x and y are measured in centimeters. Use the TI to graph the function and find the volume of the container. So this is a TI-89, but what I've done is I've actually graphed the piece function, and you know how to enter this on your calculator. My window, of course, is probably from 0 to 15. And so this is the graph that you get. So what happens is I have two different functions in effect, right? Because I have a piece function. So I have the green portion of it, and then I have this horizontal. So the green is the top part, and then the horizontal line is the y equals 2.95. So here it's totally flat. So here, I mean, I can do integral, but really it's just a rectangle, okay? However, this part is not. So this part, when you're revolving it about, so this rectangle, when you revolve it, will give a cylinder. But anyways, axis of rotation, x-axis, perpendicular, it's going to be a disk. And so now I actually did this one with an integral. So this will be, it's dx, right? The height is x, so it'll be x0 to x equals 11.5, and the radius will be the y1 coordinate, which you'll have to change to in terms of x, and y1, of course, is that ugly radical function. The other piece goes from 11.5 to 15. So there's your pi, radius squared dx again, and your radius anywhere here is 2.5 because it's flat. Okay? And there's your and the actual solid you would get would be this, kind of like a wine bottle. Okay, I believe this really and truly is the last one. Yes, it is. Okay, so last one, and then last video on chapter 7 will be cross sections. So region bounded by y equals 9 minus x squared, which of course is negative x squared plus 9, which would be that. Y equals 0, which is the x-axis, x equals 2, and x equals 3. So we're talking about this little shaded region right here. We're going to revolve it about the y-axis. So we have to have a horizontal strip. It's going to be a washer, big R squared minus little r squared. The height is vertical, so it's dy. So this has to go from the bottom of the shaded region, which is y equals 0, to the top. You'll have to plug 2 into this function to find out that it's the y coordinate there is 5. Then your big radius, which goes from here all the way to here, is the x coordinate of that point, minus your little radius, of course, is just 2. And of course, you have to change that x back in terms of y. But really, you have x squared. So if I just take this equation and isolate x squared, that x squared becomes 9 minus y. And there's no square there. Let me get rid of that, because x squared is 9 minus y. Okay, and that is the